everyone, welcome to the chemistry channel. So today I'm going to be showing you how to derive this equation. And I'm going to be doing it using calculus. So this is sort of like the one derivation I did in the last video, but where I did it algebraically. However, in this video I'm going to go more deeply into the mathematical description of heat capacity and how to derive this equation. So let's begin with our definition of heat capacity, where C, which is heat capacity, is equal to dQ over dt. Now dQ is the heat lost or gained by the object, and dt is the change in temperature of the object, and then C is the heat capacity. And there's actually two types of heat capacity, and we're going to go over the first one, which is the one that we used in the last video. So this one is the constant pressure heat capacity. So when it's under constant pressure. So constant pressure heat capacity can be found by doing this. So remember that our first law states that du is equal to dq plus dw. And we're going to assume a reversible system, allowing us to do this. And then we're going to assume constant pressure, which gives us this. So we're going to integrate our first law with constant pressure in mind. And when we integrate this, we get change in U is equal to Q minus P times the change in V. And you may remember that when we are at constant pressure, we're first going to solve for Q. So Q is equal to delta U plus P times delta V. And since we're under constant pressure, we know that delta H is equal to Q, which is equal to du plus P change in V. So delta H is equal to delta Q. So therefore, we can replace, so we'll bring back our little equation here. We can replace our dq with dH if it's under constant pressure. And when we do this, when it's under constant pressure, we get this expression. And this is involving partial derivatives because we're keeping one variable constant, and in this case, pressure. And so this we denote as Cp. The second type is under constant volume. Now, when we're under constant volume, let's bring back our first law. And now under constant volume, dW is equal to 0 because dV is equal to 0. So therefore, du is equal to dQ. Now this allows us to substitute in our heat capacity equation. Now remember, our heat capacity equation is this. I'm sorry about that. Let's get this out of here. So this is our original heat capacity equation. And since under constant volume, dQ is equal to du, we come up with another form of heat capacity. Which is this form. Now note that these two forms of heat capacity do not give the same values. we're not going to get into that because it's not relevant for general chemistry. Most of general chemistry uses CP values. So now what we're going to do is we're going to derive the Q is equal to mCp times delta T. So we're going to bring in our CP equation. And we know from the last video that Cp is equal to N times Cp bar. And remember that Cp bar is just the molar heat capacity. So therefore, N times Cp bar is equal to dH over dt holding pressure constant. Now we're going to solve for dH, so N Cp bar times dt is equal to dH. Now what we're going to do is we're going to assume that Cp is constant. Now Cp is sometimes not a constant, however in general chemistry it is, usually. So therefore we can take it, when we integrate it, we can take it out of the integral. So when we integrate this, we get change in H is equal to N Cp bar times the change in T. Now remember, we're under constant pressure here. So therefore, dH is equal to Q, which is equal to N Cp bar change in T. Now remember that this is the molar heat capacity. And this has the units of joules per Kelvin times mole, or Celsius. It could be Celsius as well. The other form is called the specific heat. So in this case, you'd have delta H is equal to Q, which is equal to N M times Cp bar dt, where the Cp bar here is joules per Kelvin times grams. So this is the more common version of it. And now remember that negative Q of the reaction is equal to Q of the water. And since negative Q of the reaction is under constant pressure, we can say that negative delta H of the reaction is equal to negative Q of the reaction, which is equal to Q of the water. Therefore, we can substitute in our equation, which gives us negative delta H of the reaction is equal to negative Q of the reaction, which is equal to M of the water times the specific heat of the water times the change in temperature of the water. And then if you just want to solve for delta H of the reaction, divide by -1, giving you delta H of the reaction is equal to Q of the reaction, which is equal to negative M H2O, mass of H2O, times Cp bar of H2O times delta T of H2O. And that is how you derive this equation using calculus. So I hope you found that interesting or helped you understand a little better. And in the next video, as I said in the last one, we are going to be talking about the bomb calorimeter. So I hope to see you all there. Thank you for watching.